Okay, difference equations. So these are inhomogeneous first order difference equations. The approach is more or less the same, but instead of having your standard homogeneous difference equation, there'll be another function attached to it, and that function will have its own solution that needs to be added on to the solution to the homogeneous difference equation. That may not make sense, but hopefully it will by the end of this video. So let's start. This is what they look like. So we could have a difference equation when rearranged, might look like this. And you can see that there are two parts to it. There's the u of n is equal to 3 times u of n minus 1. That's the homogeneous part, and we would have covered that sort of difference equations in the previous videos. Then there's this added part on after it, the n minus 5, that has to be dealt with separately. And we'll have a solution for each of those two parts on the right hand side, and we add those solutions together and solve some equations just as before. So the green part for all these videos will be the homogeneous part, and this thing then will be the additional function, and we'll add the solution for the homogeneous part to the solution for the function there underlined in red. Or you might have something that looks like this. Again, we'll rearrange it to look like something we had before. The underlined green part is what you would have seen before with homogeneous equations, and then we have this additional function after it. And once more, you'd have to get a solution for the thing underlined in green and a solution for the thing underlined in red, and we'd add those general solutions together, get some equations, and solve the simultaneous equations. The last type of example looks like that. Again, I haven't changed it there, but the homogeneous part is the first part, and the thing that makes it inhomogeneous is the function at the end of it, and we need a solution to both of those added together to give us the solution for the inhomogeneous difference equations. Alright, so I'm basically saying you'll get a general solution for the entire thing by getting the solution for the thing underlined in green and adding together the solution to the additional functions. Alright, so where do we go from here? After this, we take a look at the solutions to the additional functions. And this is quite straightforward as well, although it may appear complicated at first. So again, for an inhomogeneous differential equation, it's a homogeneous equation plus an additional function. And when we try to find the general solution for the inhomogeneous equation, we need the general solution for the homogeneous part and the additional function. And we're dealing with the second thing now. Alright, so I'm going to look at the first and the last column to start with. So if we had the homogeneous function plus a constant, its solution will just have a constant a in it. If the additional function at the end looked like the equation of a line, so kn or kn plus c, then the particular solution will be an equation of the line, a plus bn, where a and b are constants. If the additional function was in the form of a quadratic, so kn squared or kn squared plus ln, or kn squared plus ln plus m, then your solution as well will be in the form of a quadratic. And n here is the variable. Or if your function at the end is in the form of an exponential, so a constant by p, and then the variable is up to the power, your solution will also be an exponential function. And we just generalize it there by having a constant a plus another constant b by a constant p, all to the power of n. Now if we look at the middle column, what I'm basically saying is the highest power of n dictates whether it's a constant, whether you've got an equation of the line, a quadratic, or an exponential. So if there is no n next to the inhomogeneous, if there is no n next to the homogeneous part of the inhomogeneous solution, that's a mouthful, then you're just going to have a constant. If the additional function has got an n to the power of 1 as the highest power of n, then it's a line, so that's going to mean you're going to have the line solution. If the highest power is 2, it's quadratic, so you'll have a quadratic solution. And if n is the power, it means you'll have an exponential solution. Again, that may not make sense. Hopefully the next slide will clarify that further. So we start with the exact same thing. And let's say you have a function that looks like that. So the first part is the homogeneous part, and we know what that solution is already. The second part looks like it's in the form of the equation of a line, because n to the power of 1 is the highest power of n. So the general solution for that will look like this. So the homogeneous part, that's the 3u to the n minus 1, its solution looks like a bracket 3 to the power of n minus 1. And then the red part, the equation of the line part, will have an equation of the line as part of the solution there as well. So the entire thing in the handwritten box will be the solution to the inhomogeneous difference equation. You'll notice there we have 3 variables, and if that's the case, we'll need 3 equations to solve for those and 3 values as well. So probably u of 1, u of 2, and u of 3. So 2 more examples. If your difference equation looked like that, the thing underlined in green, 2u of n to the minus 1, that's your homogeneous part. It has a homogeneous solution to it. The thing underlined in red, the highest power of n is 2, so that means it's a quadratic form. And then we're going to add the 2 solutions for the thing in red and the thing in green together to give us something like that. So the green part, the homogeneous part, the general solution there is a, and then 2 to the power of n minus 1. And then the thing after it will be the solution for the extra function at the end of the text that is obviously printed or typed in a Keynote here or on the computer. Third example, we can see again that the homogeneous part is 2u of n minus 1, so that'll have a solution of a bracket 2 to the n minus 1. And then the underlined red part is your additional function, and its solution will look like that. Now, hopefully it makes a bit more sense. I'm going to show you 2 examples, and if that doesn't clarify anything, clarify anything further, then you can just talk to me directly. Okay, so first thing, the question reads, solve the following. It's u of n minus 2u of n minus 1 is equal to n, and we're given an initial condition of u of 0 equals 1. Now I've rewritten it to be u of n is equal to 2u of n minus 1 plus n. And the first thing you'll notice, there's a line under the first part and a squiggly line under the n. So the line is the homogeneous part, and the squiggle is the additional function. Each of those have their own solution. So the homogeneous part gives me the a, and then 2 to the power of n minus 1, where the 2 is just coming from the 2 in the u of n is equal to 2 u of n minus 1 plus n. The squiggly line then, it has its own solution, and that's underlined with another squiggly line. That's our starting point. Once you form that, then we need to solve for the values of big A, small a, and n. So we have 3 unknowns, meaning we need to find 2 additional initial conditions. We have u of 0 already. We now need to find u of 1 and u of 2 as well. So there's a bit of rough work. I'm going to sub u of 0 into the equation with the green and red underlining it. So we get u of 1 there in the second equation line is equal to 2 times u of 0 plus 1. But sure, we know that u of 0 is 1, so it's 2 times 1 plus 1, which is 3. To get u of 2, it's 2 times u of 1, so that's 2 times 3. Add 2 to that is 8. So I have my 3 initial conditions. And then what we need to do is take the general solution and start subbing in n is equal to 0, n is equal to 1, n is equal to 2. Right, so let's give it a go. U of 0, when we put n equals 0 into the general solution equation, we get the first equation there. When we put 1 in instead of n in the general solution equation, we end up with equation 2. And then if we fill n is equal to 2 into the general solution equation, we get equation 3. And we need to solve for big A, small a, and b. Now, I've done it really quickly. If you put equation 2 and 3 together, if you multiply equation 2 by minus 1, big A and b cancel, and you get a is equal to minus 2 straight away. Sub that into equation 1, you get big A is equal to 6. And sub both of those into equation 2, and you get b is equal to minus 1. And you just take your big A, big B, and small a, and sub those into the general solution again to get that. And that's the solution to the inhomogeneous difference equation. Okay, example 2. All right, so we have the homogeneous part and the inhomogeneous part. The homogeneous part is minus 3u to the n, and then the additional function there is n squared minus 2n plus 1, and the presence of that makes it an inhomogeneous difference equation. All right, so we get the solution for each of those, and we add them together. So the solution, first of all, for the function there, it's a quadratic, so we have a quadratic solution. And then for the homogeneous part, that's your solution there. We'll add those together, it gives me that. Okay, how many values do we need to find? Small a, small b, small c, and big A. So we have 4 values, so we need to find 4 initial conditions: u1, u2, u3, and u4. And we go to that first difference equation. That's the thing that says solve the inhomogeneous first order difference equation. U of n plus 1 is equal to n squared minus 2n plus 1 minus 3 u of n. We go there, we fill in 2 for, we fill in, we get u of 2 is equal to 1 squared minus 2 to the 1 plus 1 minus 3 u of 0. That will give me a value. Find u of 2, u of 3, and u of 4, and they're done there in the bottom right-hand corner. Once we have those, we go back to the box there on the bottom left-hand corner. That's the general solution of the inhomogeneous difference equation. And we fill in n is equal to 1 to get one equation, n is equal to 2, n is equal to 3, n is equal to 4. We get 4 equations. So when we do that, we get 4 equations. You can see those in the first 4 lines there in that box. They're labeled A, B, C, and D on the right-hand side of that. And basically, you need to solve those for those values. Now, you do all the maths, and then once you have A, B, C, and D, you put it into the formula for the solution of the inhomogeneous difference equation, which has that bold black line around it right at the top, and it gives you that equation there. Okay, time for some questions.